Welcome to Empowered Learning. This is the third video in the video series on reviewing sequences for its use in calculus. So this third video will be the video where we do a lot of examples. And of course, these examples are going to consist of mainly listing out the first few terms or so of a sequence, taking a sequence in its numerical listed form, and from that being able to construct what the sequence would be in algebraic form, and then determining whether a sequence that's already in its algebraic form is going to converge or not. And so that's really the main aim of these examples. So let's go ahead and start off with this first example. So pretty simple. We just want to list out the first 6 terms of this recursive sequence here. And if you remember from the part 1 video that we did, a recursive sequence is just a sequence where we have the first, let's say 1, 2, or 3 terms or so is predefined for us, and then the remaining terms are calculated or figured out by previous terms. Okay, so we see here that this is the term that is predefined for us. So we know that the first number in our sequence is going to be 8. So the second number in our sequence, we'll need to use this formula here to be able to calculate it. Okay. So at first glance, this may seem like we just need to plug in a 2 here and a 2 here and a 2 here, and we just go to work. But you're going to see that that doesn't make a whole lot of sense for us here, because if we actually did that, then this would basically saying that we have a value of A3 is going to be -1. Let me get that looking a little better here. So this would be -1 raised to the 2 minus 1, which would be this, times a sub 2 over 2. And the problem is we don't even know what a sub 2 is, and we're really not looking for A3, we're looking for A2. Okay, so what we need to do here is make sure that we understand exactly what this formula for the sequence of numbers that comes after 8 is trying to do for us. Okay, so how I'm going to write this to make sure that we fully understand what's going on. We know that we are trying to find a sub 2, which is the same as a sub 1 plus 1. Okay, so in this case, even though this is the second number in our sequence in terms of n, this is when n is equal to 1. So this is the first number that we're actually tracking values by using the subset of the natural numbers. Okay. So because of that, we're going to use this formula as if n is 1 to find out A2. So if we do that, this will be a -1 raised to the 1 minus 1 times a sub 1 divided by 2. And if you notice there, we do know what the value of a sub 1 is, and that's just going to be 8. Okay, so this works out just fine. So here we have -1 raised to the 0 times 8 divided by 2. And of course, here we know that anything raised to the 0 here is just going to be 1 itself. And 8 divided by 2 is just going to be 4. So our final answer for here ends up being a positive 4. Okay. And so now from there, the rest of these are going to be relatively easy to calculate. Okay, so we have a sub 3, which is going to be a sub 2 plus 1, which is going to be a -1 raised to the 2 minus 1 times a sub 2 divided by 2. And of course, -1 raised to the 2 minus 1 is just going to be a -1. And We know that a sub 2 is 4. So we take 4 divided by 2. Final answer is a negative 2. And so then I'll just go ahead and write the rest of them. Follow suit. So a sub 4 is the same as a sub 3 plus 1. So of course, in this case, n is equal to 3. And this last one, n was equal to 2. Make that look like that. So we got 3 minus 1. A sub 3 divided by 2. And of course, it was negative this go round. So that means this next go round is going to be positive. And we have a sub 3, which was negative 2 divided by 2. So this will end up being a negative 1 this go round, okay? And we continue on. So we got a sub 5, which is a sub 4 plus 1. So n is actually equal to 4 in this case. And so, of course, negative 1 raised to an odd number is going to be negative 1. And a sub 4 is a minus 1 divided by 2. That ends up being a positive 1/2. And, of course, for the last one, we have a sub 6 is the same as a sub 5 plus 1. So here this means that n is equal to 5. And of course here, negative 1 raised to the 5 minus 1, that's just going to be a positive 1. And a sub 5, of course, is 1/2. We divide that by 2, and we see that we end up getting a positive 1/4. So that is how we would actually interpret this recursive sequence here to be able to figure out the first 6 terms of it, okay? And of course, the main thing was being able to figure out, well, how do I actually figure out what a sub 2 is, or the second number in the actual sequence? And once you translate that right, everything else just comes easy. All right, so let's look at another example. So for this example, what we want to do is find a formula for the nth term of the sequence where a sub n is calculated directly from the value of n. So that's just a fancy way of saying we have the sequence, write it algebraically as a function of n, okay? So, of course, you can see here we have negative 9, 9, negative 9, 9. So we definitely see that we have some kind of alternating sequence thing as far as the signs are concerned in there. So we're going to list out a few terms just to kind of get an idea of what this is exactly, okay? So since we have a negative 9 here, this would be the same as if we had a negative 1 times 9. And since this is 1, we could look at this as negative 1 raised to the 1 times 9. And actually, to make that look a little better, I'll write it this way. So we'll just say negative 1 raised to the 1 times 9, like that, okay? And since this is the first number in the sequence, n is equal to 1 here, so I could look at this like it's negative 1 raised to the n times 9. And hopefully, when we list out a couple more of these numbers here, we'll be able to get the same pattern. So we have a sub 2, which is going to be a positive 9, which will be negative 1 raised to the positive 2. We know negative 1 raised to an even number is always positive. Multiply that times 9. And we see here that we can also rewrite this as negative 1 raised to the n times 9. So let's do it with a sub 3. That's going to be negative 9 again. And this time, since n is going to be equal to 3 here, then we would raise this negative 1 to the power of 3. And of course, anytime we have negative number raised to an odd number, we know that the result ends up being negative. And so it didn't quite work out there. So we see that we're pretty much following the same pattern here. Okay, so we're good to go. So what this tells us is that the sequence a sub n could be expressed as a sequence of numbers that can algebraically be expressed this way. Okay, and so that was the point of that example, to show how we could actually take a simple sequence like that and express it in terms of n, where n is a subset of the natural numbers. All right, so let's look at this next example. So we have a list of numbers, and we see that this list of numbers is basically going to be a sequence, and we want to be able to algebraically try to describe what's going on with these numbers here. Okay, so to start off, you see some kind of similarity in the numerator and denominator here. Of course, in the numerator, we see 1, 2, 2 raised to the 2, 2 raised to the 3, 2 raised to the 4. Okay. Now, if we're trying to keep it in the same, well, the numerator part, if we're trying to keep this in the same profile as what's going on, or the same pattern as what's going on in the numerator, I could look at 2 as 2 raised to the 1. I could also look at 1 as 2 raised to the 0. So if that's the case, 2 raised to the 0, 2 raised to the 1, 2 raised to the 2, 2 raised to the 3, 2 raised to the 4, we kind of got a pattern going there. Okay. Now, we also see here that in the denominator, I have a 10, and of course, each number after that is just 5 more than it was for the previous number. Okay. So in seeing that, we see that we have a nice way of being able to kind of imagine what's going on here, but we're going to formally list out a few terms to try to see what this pattern is going to look like algebraically. Okay, so let's look at the first number in the sequence, which we know is 1 over 10, but can be expressed as 2 raised to the 0. And here we know that this is going to be, 10. Now, of course, I'll just write it as 10 for now. And so here, I'll just leave this like that for right now. All right, so let's go to a sub 2. We know that this is 2 over 15. And this is the same as 2 raised to the 1. And of course, one way that we could look at this is 10 plus 5. Okay. Now, with these two, notice that here I want to be able to express the denominator in terms of 1 or n this time. Okay. So I could say 2 raised to the 0 times 10 times 1. But of course, when I come down here, it's not going to make sense for me to say 2 raised to 1 divided by 10 times 2, because that's not going to give me 15. Okay. I'll also see here that if I try to somehow rework this to where I have 15 is equal to something with an n, and n will be equal to 2, leaving it in this form is not going to help me much. Okay. So the point that I'm trying to get at is we do have to be a little bit creative in the pattern that we come up with. Now, one thing that we do know is that 10 is the same as 5 times 2. So if I come here and I say, all right, well, this is the same as 5 times 2. And then here I know that 2 could be expressed as 1 plus 1. Then here I have a way for me to express both 0 and 1 in terms of n. And so what I'm going to do here is, since this is a 1, I could express this as 1 minus 1 like that. 5, 1 plus 1. And I'm going to let one of these number ones in the numerator and denominator be substituted by n. Okay. So I could come up with a pattern that way. Now, let's look and see if we can do the same sort of thing with a sub 2. So here we know that the numerator again can be expressed as 2 raised to the 1. And now we're going to express the denominator as 5 times 3. Okay. But of course, we know that 1 could be expressed as 2 minus 1. And here we know that 5 times 3 could be expressed as 5 times 2 plus 1. And again, since my n is going to be 2 here, I can let my 2's be replaced by n's. And what you're starting to see is that we have a pattern that may work. So I'm going to list, try to figure out what A3 is to see if it will also follow suit. Okay. So here I could rewrite 2 raised to the 2 as 2 raised to the 3 minus 1. Okay. And the denominator here, this will be 5 times 4. And of course, 4 is the same as 3 plus 1. And of course, since n is 3 here, we'll let anything that says 3, replace it with n. And you're seeing that, yep, we have something that will actually work as far as a pattern is concerned. Okay. So for that reason, we know here that if we went down to the nth term in the sequence, this would just look like 2 raised to the n minus 1 over 5 times n plus 1. So what we say here is that our sequence, and I'm putting the set braces there to let us know that, yep, we're actually talking about a list of numbers here. I want to say the set of numbers that if we listed it out, they would all follow this particular pattern here. Okay. All right, and that would be the answer to this example. So let's move on to the next example. So this next example, same sort of thing. The one thing that's different now is that, of course, the numbers are different, but the way it looks is pretty much the same. Okay. So we look here, and one of the things that should jump out at us is the denominators for these numbers here. Okay. So we got 1, 2, 6, 24, 120. If it doesn't jump out at you, then hopefully after I tell you this, it will. So the numbers 1, 2, 6, 24, 120. These are the first couple of terms in the sequence better known as a factorial. Okay. So here, if you remember, 1 factorial is 1. 2 factorial is just 2 times 1. Which is 2. 3 factorial, which is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which if we multiply all that is just 6 times 4, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is just basically the same as 24 times 5, and that'll give us 120. Okay, so you see how we have 1, 2, 6, 24, and 20 for the first 1, 2, 3, 4, 5 numbers in the factorial recursive sequence. So we know that for our denominator here, if I was to say, well, what is this set of numbers going to look like? I know my denominator is going to look like n factorial. Okay. Now, my numerator, if you notice, I have 5, 8, 11, 14, 17. All these numbers have a common difference of 3. So that lets me know that the numerator is sort of looking like an arithmetic sequence. Okay. And if you remember, for an arithmetic sequence, we know that to describe the nth term in that sequence, it would be whatever the initial number is plus n minus 1 times d, where d is the common difference. In this case, we have our a sub 1 would be 5, and our d here would be 3. So we got that. So, of course, here we would have 5 plus n minus 1 times d, which in this case would be 3. And so in general, that is what any number in this particular sequence would look like. So the only thing I really need to do now to clean this up is to figure out, well, what is 5 plus n minus 1 times 3? Okay. So here, let's say, therefore, 5 plus n minus 1 times 3, all that over n factorial. It's just going to be 5 plus 3n minus 3 over n factorial, which 5 minus 3 is just 2. So it'll be 3n plus 2 over n factorial. And so this would be the sequence in its algebraic form that would represent each number in the sequence. So we could call this a sub n here, and therefore the actual sequence, putting it in set notation form, would actually be set of all numbers that have this pattern of 3n plus 2 divided by n factorial. Okay, and so that is how that particular example works and what the final answer is for that one. So in general, what I'm trying to illustrate through these first few examples is that we can figure out what the algebraic form of a sequence is by either listing out the terms until we see a pattern, or if we recognize a pattern, we can kind of do like how I did here, is sort of try to piece the pattern together. And then if we need to do any simplifications, you can do that. Okay. All right, so let's move on to our next example. So we're going to switch gears a bit, and instead of trying to find out the list of the first few terms of a sequence, or trying to figure out, well, how can we express this sequence as a function of natural numbers, we're now going to take sequences that are already expressed as a function of natural numbers, and we want to see whether those sequences converge or not. Okay. Remember that when a sequence converges, all that means is that if we have a list of numbers, as we list more and more numbers, it looks like that the end of that list is trying to approach some specific number, okay, specific real number. If it diverges, then that means that we either have a situation where the numbers keep getting larger and larger, positively speaking, as n approaches infinity, or the numbers keep on getting smaller and smaller and smaller, negatively speaking, down to negative infinity, or we have a situation where we just have stuff going back and forth, kind of like if we listed, let's say we had, -1, +1, -1, +1, that alternating sequence. If we try to take the limit of that as n approaches infinity, we wouldn't be able to answer that question. So that would be a D&E type situation. Okay. So essentially what we are going to do to figure out whether these sequences actually converge or not is we're going to study the behavior of its corresponding real valued continuous function. Okay. So for this first example here, we know that 4 plus 0.2 raised to the n, that can also be expressed as 4 plus 1/5 raised to the n. This has a corresponding real valued function that is 4 plus 1/5 raised to the x. Okay, where x is any real number. So we have this corresponding function here, and we know from basic fact number 1 that we talked about in the part 2 video that the way that this particular sequence is going to behave will be the exact same way that this particular function behaves. So if we want to know whether this sequence converges or not, we need to see, does the behavior of this real valued function, a real valued continuous function, does it converge upon some specific real number or not? Another way of saying that, if we take the limit of this real valued continuous function as x approaches infinity, is the limit going to exist? Meaning, are we going to get a real number for an answer? And that's what we need to figure out here. Okay. So here, if this particular sequence a sub n, well, no, let me say it like this. So basically what I'm trying to say here, and I wanted to write it, but I'm not going to write it. So if the limit of this function here as x approaches infinity, if it exists, then it means that this particular sequence here will converge. Okay. So we're just going to evaluate the limit to see, does that actually happen? So we're going to do limit as n approaches infinity of this particular function here. Okay. Now, one of the things, we could get real fancy here in trying to do this, but at the end of the day, I'm going to use pre-calculus knowledge to try to get us to the answer in a more efficient manner. So we know here that I could just plug in this raised to the infinity. Okay. And so, and that should be a x, not an n. So let's switch that right quick. All right, so in general, we know that 1/5 raised to the x, this is an exponentially decreasing function. So if we actually looked at a graph of this function here, it would be going like this. So as x gets closer to infinity, my y values for 1/5 raised to the x are getting closer and closer to 0. So all of this goes to 0, which means that my final answer for that particular limit is 4. Okay. And so therefore, because the limit as x approaches infinity of this particular real valued continuous function, since the limit actually ended up equaling a real number, which is another way of saying that the limit exists, this implies that the limit of this corresponding sequence is going to be equal to that same real number. Okay. So it's going to be 1/5 raised to the n. That is also going to be equal to 4. And since that limit exists, then we know that the sequence A sub n converges. Because of the fact that, hey, since this limit existed, then that follows that this corresponding limit existed. And whenever you have the limit of a sequence as n approaches infinity equaling some real number or existing, we know that that sequence converges. Okay. All right, so let's look at our second example. Different sequence, same idea. Okay. So here we want to figure out whether this sequence is going to converge. We are going to consider this corresponding function. And all I'm doing is just replacing the n's with x's, and I'm assuming here that x could be any real number that's in the domain of this function. Okay. So of course, I know I wouldn't be able to plug in 0 here because of the denominators, but pretty much anything else I can plug in. Okay. So what I need to study here is the limit as x approaches infinity of this corresponding continuous real valued function here. Okay. I'm going to write it like this. And so if the limit of this particular real value continuous function, if it exists, then that means that the limit of the corresponding sequence, which we have here, is going to exist as n approaches infinity, which means that the sequence is going to be convergent. Okay. All right, so to be able to evaluate the limit of this particular function, what I'm going to do is just separate this into two separate limits using my limit laws. Okay, so for the first limit here, we know if we plug in infinity, we're going to get infinity over infinity. But instead of me, trying to do Hopital's rule and all that, I'm going to just simplify this. And this is going to look like 1/8 plus 7 over 8x. And then I'll rewrite what I have here the same way. So now that we look at this, if I evaluate this limit, I can have 1/8 plus 7 divided by 8 times infinity. And all that is multiplied by 1 over 7 divided by infinity. And of course here, any number divided by infinity, limit-wise, is going to go to 0. So all that is going to 0 here. 7 divided by infinity goes to 0. So all I have left is 1/8 in that first product, and I have 1 in the second product. So the answer to that limit is 1/8. And since 1/8 is a real number, then what that means here is that this particular limit exists, which means the limit of the corresponding sequence as n approaches infinity is also going to exist as well. All right, so from here, I'm running out of room here. Just going to basically say from all of this that we know that limit as n approaches infinity of n plus 7 divided by 8n times 1 over 7 divided by n, all that's going to equal to 1/8. And therefore, this sequence S of n converges. Okay. So for our next example, we want to do the same thing. We want to see whether this particular sequence will converge or not. And so for this example, of course, we're just going to kind of cut to the chase. We know that if we were to look at the limit as x approaches infinity of this particular function, we would want to know, is that going to exist or not? Okay. If it does, then of course, the corresponding limit for the sequence will converge. And if a limit to the sequence, if the limit of the sequence exists, then that means that the corresponding sequence will converge. Okay. So the main idea is this sequence is going to follow the basic behavior of this real valued function inside of this limit. And we want to see, does that particular limit exist or not? If it does, we know that the limit of the sequence will also exist, which means that the sequence itself will converge. Okay. Now, looking here, hopefully you recognize that from your first year calculus course, that if I was to plug in infinity in for x here and here, what I would end up with is 1 divided by 3 over infinity, all that raised to the infinity. And of course, anything divided by infinity is going to be 0. So I would have a 1 divided by infinity. And contrary to popular belief, the answer to that is not infinity. Okay, that is an indeterminate form, and we call it indeterminate power. And so in your first year calculus courses, one of the things that you should have went over is how to deal with indeterminate forms of this type. It's taught along with the concept of Hopital's rule. Okay, so in short, whenever we have these indeterminate powers here, what we do is we're going to consider naming f of x. We're going to look at it like this. Yeah, I'll write it this way. We're going to consider looking at this as f of x raised to the g of x. So we look at it like that. And the idea is that we want to take the natural log of this particular function on both sides of it. And for simplicity here, I'm going to just rewrite this as, let's say, h of x to make it simple. And what we want to do here is say, all right, well, let's do natural log of h of x. And this, if we did that, did natural log on both sides, we're going to have something that looks like this. And of course, on the right-hand side, what we're going to end up having is x times natural log of 1 minus 3 divided by x. And so the point here is that it's the infinity that's in the exponent that's giving us the issue. So what we need to do is to get this into another form. And what this ends up being by default is the infinity times 0, or some people may call it the 0 times infinity indeterminate form. Okay. And so we know that whenever we have 0 times infinity or infinity times 0, as it'll be in this case, how we get this into a form where we can actually use Hopital's rule is, let's say the function that the infinity came from, if we call that f and we call the one that the 0 came from g, we're either going to take f times g and express it as f divided by 1 over g, or we're going to express it as g divided by 1 over f. Okay. So in other words, note that 1 divided by 1 divided by g is just g, and 1 divided by 1 divided by f is just f. So we're just rewriting it so that in this case, if we were to rewrite the g, this would end up being an infinity over infinity. And here, if we were rewriting the f, this would be a 0 divided by 0. In both cases, that is going to give us, get us to a point to where we can actually use Hopital's rule. Okay. Now, in the situation that we have, probably the easiest thing to do, in my opinion, is to rewrite this x as 1 divided by 1 divided by x. Okay. And then, of course, we'll perform Hopital's rule on that particular result. So here I'm going to rewrite this as natural log of 1 minus 3 over x. And this will be just 1 over x raised to the negative 1. And that's another way of saying 1 divided by, well, this x raised to negative 1 is the same as 1 over x. So we're going to look at it that way, okay? So the point here is that we are going to indirectly figure out what the limit of this actual function is here by first actually taking the limit of the natural log of that function, okay? So here we're going to say limit as x approaches infinity of the natural log of h of x is going to be the same as limit as x approaches infinity of all the stuff that I've written here. Okay. Now, if I was to plug in infinity in for x here and infinity in for x here, you're going to see that what we end up getting here is either a 0 over 0 or infinity over infinity case. And I'll go ahead and show that to you now. So if I was to plug that in, I would have infinity here, and this would be 1 over infinity basically, okay? And of course, 1 over infinity in terms of limits is 0. 3 divided by infinity in terms of limits is 0. And natural log of 1 is 0. So we would have a 0 divided by 0 case, which is one of the two indeterminate forms that we need for Hopital's rule, okay? So my point in saying all this is that we kind of already knew that when we were here. So what we need to do now is perform Hopital's rule on this particular limit and try to evaluate it again and move on from there. So I'm going to erase what I have here in brown, and then we'll continue on and actually evaluate this limit the way that we're supposed to by using Hopital's rule. All right, so we have that erased, and now we know that we need to perform Hopital's rule, which essentially says we need to take the derivative of the numerator and denominator respectively, okay? So if we do that, we know that this is going to be 1 over 1 minus 3 divided by x. And then since this is a composition function, we need to take the derivative of the inside function. And a derivative of 1 is just 0. The derivative of a negative 3x raised to the negative 1, which is essentially what that second term is going to be a positive 3 times x raised to the negative 2. Okay. Now in the denominator, we know that the derivative of x raised to the negative 1 is just going to be a negative x raised to the negative 2. Negative x raised to the negative 2. Okay. And so now we are going to try to evaluate the limit again to see what we get. So looking here, we know that this x raised to the negative 2 and x raised to the negative 2, that will reduce to 1. Here, I see that I have this 3 here, so I could write this over that. So we're going to rewrite what I have now. So limit as x approaches infinity of 3 over 1 minus 3x. And all of that will be divided by -1. Of course, we could just rewrite that as just a -3 over 1 minus 3x. And then we'll have a -3. We'll actually execute the limit now. And of course, here we know that 3 raised to the infinity goes to 0. So our final answer here is going to be -3. Okay. Now, we are not done. The good thing about this is that we've answered this question. And in answering the question, we see that the limit of natural log of the function that we were originally trying to deal with goes to some real number. Okay. Now, that doesn't necessarily mean that the actual function itself, the limit of that, is going to be a real number, but it does turn out to be that in this case. Okay. So we're going to go ahead and come on down. And this will be our next example, by the way, but I'm just going to work by it. So now that we're here, what we do understand now is that since we were looking at the natural log of h of x, we know that e raised to the natural log of h of x is just going to be h of x. Okay, so that means if I was to do the limit as x approaches infinity of e raised to the natural log of h of x, then what that would tell me here is that I would essentially just have the limit as x approaches infinity of h of x. So what does that mean for me? Well, I know that for this limit here, this is the limit of a composition function, okay? And I know that I can slide this limit operator to the inside function to where now we are looking at this, okay? So all of that is just to say that the limit of what we see here in the exponent, all of that is just -3. And so what that tells me is that the limit of my actual function, which we named h of x, is a real number. Now, it is an ugly, irrational real number, but it is still a real number nonetheless. So because of that, we know, therefore, so we'll just say, hey, this is some real number here. So that means that the limit as n approaches infinity of our actual function, which I'm just going to name as h of x, that is also going to be e raised to the -3, which is also some real number. Well, and I probably shouldn't write it that way. So let me be formal here. So this is a real number. And thus, what I have here is also a real number. Okay? And so from that, that implies that, let me get this straight here, because I put h of x, but it really should be h of n, because we're actually talking about this particular sequence here. So if this is h of x, then that means h of n would just be 1 minus 3 over n, all that raised to the n. Okay, so that's what I'm referring to down here. And so because of all this, then I know that this sequence that is 1 minus 3 raised to the n, it is going to converge because of all that. Okay, so the main thing here is that we had to evaluate the limit of our corresponding real valued continuous function. And of course that took a while. We had to kind of pull back some stuff from first year calculus, but once we did that, hey, we saw that the limit ended up equaling a real number, so therefore the limit of the sequence has to follow suit. It's approaching the same number, and thus the sequence will be convergent because of that. Okay, all right, so I'm going to erase the rest of the stuff that I've written down here, and then we'll start with this next example. Okay, so for our next example here, we want to do the same thing. We want to take this sequence here and see, is it going to converge or not? And of course, we could express this sequence, the algebraic part, as natural log of n divided by 3 raised to the 1 over n. We could do that just to make it a little bit easier to deal with. And again, our approach is we want to deal with the corresponding real value continuous function part or counterpart, which would be natural log of x divided by 3 raised to the 1 divided by x. Okay, so here what we want to do is take the limit as x approaches infinity of natural log of x divided by 3 raised to the 1 over x. And of course, the idea here is that if this limit exists, then the limit of the corresponding sequence, which would be natural log of n divided by 3 raised to the 1 divided by n, as n approaches infinity, will also exist, which means that your sequence will converge. Okay, otherwise it's going to diverge. So if we look here, I'm just going to kind of take the simple approach to this. If I go ahead and substitute infinity here, and I substitute infinity here, we know that in terms of limits, 1 divided by infinity is going to go to 0. Okay, and so in knowing that, that lets me know that 3 raised to the 0 is 1. And of course, natural log of infinity, that's going to approach infinity. It'll get there very, very slow, but it will get there. Okay. And so we see here, since infinity is not a real number, then we know that what essentially ends up happening is that this particular sequence here is going to diverge. Okay, so because this is infinity here, then it follows that this particular sequence is going to also go to infinity, which means that this sequence here diverges. Okay, and so that's really the main idea here for this one. So we see one where essentially the numerator of this function grows faster than the denominator does, and because of that, as we list more numbers in the sequence, the numbers are just going to get bigger and bigger and bigger from a positive standpoint. All right, so for my last two examples, I've already written out these, and I wanted to just go ahead and go over them because there's a lot that goes on with it, and it could get a little complicated at times, but I want to try to keep it as simple as possible here. So we want to see whether this particular sequence here is going to converge or not. And so the first thing that I notice here is that we want to consider that the limit of the sequence n factorial divided by n raised to the n goes to 0. Now, where does this come from? If you go back to the part 1 video, we actually studied that particular sequence, okay? And so I'm using this sequence and its behavior as sort of a barometer to help me out with this particular sequence because it looks sort of similar, okay? So here's the main idea. If you notice here, this 5 raised to the 2n, I know that 5 raised to the 2n, if I use my exponential rules, could be looked at as 25 raised to the n, okay? And of course, 25 raised to the n is the same as n raised to the n, where n is specifically 25, okay? So the point that I'm trying to make here in all of this information that I'm writing down here is that at the end of the day, because my n is approaching infinity, there's going to be some point, some n value, and of course I'll call it like big N. There'll be some n value to where n raised to the n is going to start to grow faster than 25 raised to the n. Okay, and so the way that I actually did that is I said, all right, well, let's consider this, this sequence here, which can be rewritten like this, and then I actually listed out a bunch of terms. And so I did some investigation just to kind of prove my point here. And what we saw is that the numbers, they started to get smaller. So as you see, 0.04, 0.0032, 0.000384, they kept on getting smaller. But then at some point, sometime beyond here, we see that the numbers start to get larger again, okay? And so that showed me in a very primitive way that what ends up happening here is this particular sequence is going to eventually grow out of control. Okay, it's going to get bigger. Now, the way that I looked at it is I said, all right, well, we need to take the basically the limit of this particular function here. And we can do that by, of course, looking at the corresponding real valued continuous function if we wanted to. But since factorials really don't work like that, I didn't consider that this time. But what I did do is I say, okay, well, since I see that these numbers eventually grow out of control, this tells me that my 25 raised to the n, at some point, 25 raised to the n was larger than n factorial, but eventually it got to the point as n approaches infinity that n factorial was larger than 25 raised to the n, okay? So in other words, as n approaches infinity, I know that what happens here, excuse me, I know what happens here is that n factorial is getting larger than 25 raised to the n, okay? Now, because of that fact, we know that n factorial is going to grow faster than this, and where this whole n raised to the n part comes into play, remember, we said here that we said here that n raised to the n is always going to be larger than n factorial. So here we know that if we replace this with n raised to the n, this is going to be going to 0, but because what we actually have under or in the denominator there is something smaller than that, it's not going to be approaching 0 here, it's going to be approaching infinity. And so basically for the base here, we stopped at some value. So what that means is that since this is a constant, at some point n factorial is going to be larger than, okay? And so I tried to do this in the most simple way possible, but I wanted to do it and show you why that actually is and not just tell you, okay? All right, so for this last example, it's kind of the same thing that we did for not the last example that we just did, but for the previous two. We have a situation where we have to figure out whether this sequence is going to converge or not, and we want to consider the real valued equivalent of that particular sequence, which is going to be, in this case, 4x plus 1 divided by 4x minus 1, which is a rational function. And what we want to do here is basically, if we can show that the limit of this real valued rational function is going to exist, then that means that the limit of the sequence, corresponding sequence here, will exist, which means that the sequence will converge, okay? And so here I go through this process of evaluating the limit. And of course, if I just use my limit laws and slide my limit operators, to the inside function here, and also do with the outside, I see that I get this 1 divided by infinity indeterminate form again. So we've seen this sort of thing before. So what I need to do here is not consider this function per se, but consider the natural log of it, which is here. And so again, the purpose of this is for me to be able to take out this x here and pull it out in front after I do the natural log of both sides, which you see that here. And I know that that's automatically going to be in a 0 times infinity indeterminate form. And of course, it's easiest for me to take that x and rewrite it as 1 divided by 1 divided by x. And of course, you see that down here in the denominator. I've also taken the liberty to go ahead and rewrite natural log of 4x plus 1 divided by 4x minus 1 in as a difference of logarithms, because it's going to make it easier for me to take the derivative of it when I apply the Hopital's rule, okay? So we do all this. So that means if we try to take the limit of the natural log of that function, we're going to have the 0 divided by 0 case. So we now know that we can use the Hopital's rule. At this point, I'm basically going to look at this function here and take the derivative of the numerator and denominator separately, which is what I do right here. I simplify, which is what you see me going on there. And then just trying to get it into a form where I can actually evaluate the limit again, okay? So I do all my simplification here, and then eventually I get to 1/2, okay? So I know that the limit of the natural log of what I was originally trying to find the limit for is just going to be 1/2, okay? So if you remember in the other problem that we had that kind of had the indeterminate form, we know that to find out the limit of the actual function, we would have to do the limit of e raised to the natural log of y. And of course, our logarithm properties let us know that e raised to the natural log of y is just y itself. And here I could slide this limit operator on the inside. And I know that all this business here is just 1/2 because that's what we found here. And so therefore, the limit to the actual real valued continuous function is just going to be square root of e, or e raised to the 1/2. Thus, we know that the limit of the corresponding real valued continuous function is a real number. So therefore, limit of the sequence follows suit. And because of that, we know that our original sequence that we were considering converges, okay? All right, so with that being said, this concludes the series of videos on reviewing sequences and showing how we actually use them in a very basic sense in calculus. So the next set of videos that you probably should be watching if you're kind of following along here should be videos on series. And so hopefully I'll have those up in a few days or so so that you can watch those. And I hope these videos helped. Take care.